Okay, it's me again. I've got something to celebrate. I just got this message. Good job, Jean-Louis. Your research items reached 50,000 reads. As an amateur physicist, I think that's kind of neat. Um, Basically, I want to talk a little bit, not about what makes sense and what doesn't make sense, but from my experience, I'm 55 years old, and we're all interested in the same. We're amateur physicists. We're trying to make sense of all these new theories, I would say. And I make this video not to say like this is the ultimate theory, because I think there is no ultimate theory. I'm sharing this to this is kind of neat. I googled my name and I see that some of these explanations that I come up with, like for explaining the anomaly of the magnetic moment and what the fine structure constant actually is. Many look at it as a very magical number. Let me see. Any case, the people pick things up, and I've published first on Vixra, and people still seem to quote that also. The quark gluon model, or I would say this paper, of which I'm proud and at the same time a little bit ashamed. It's probably my most I wouldn't say violent, but most critical obstacle that I encountered when trying to study physics and understanding what quarks and gluons actually are. And so that's what I want to talk a little bit about now. You're probably very much the same like I am, where you really think, okay, I want to understand physics, so I'm going to study classical electromagnetic theory and the Planck-Einstein law, and then you move to quantum electrodynamics or quantum field theory, and then you move to quantum chromodynamics. And I got stuck, and I think most people will get stuck, and that's probably the crisis of physics, where once you start reading about the theories that developed since the Second World War, you realize that a lot of it is what I call smoking gun physics. We have these particle accelerators, CERNs, beautiful pictures, and then you look at sort of, okay, where are the quarks? Because I only see jets of particles. Where are the Higgs bosons? And then you do realize that there's a big gap between the theories that are used to explain certain experimental measurements, and it's all phrased in terms of what quantum physics is phrased in terms of probabilities. Well, the likelihood that the W or Z boson is being seen in this image is 90.50% higher than another equivalent theory, and that's sort of the message I want to give, and it's a happy message. So let me go to the structure of the video presentation a little bit. So my trajectory was very much indeed this, and that I sort of studied classical quantum mechanics or classical physics using Feynman's lectures, other textbooks, and then you sort of see from the 70s the quark gluon hypothesis, QED, QFT, and then the weirder theory, supersymmetry. What is symmetry? And then quantum gravity. And then you do get that feeling that Paul Ehrenfest described. It is a bit like an unendlicher Heisenberg, Born, Dirac, Schrödinger, Wurst Maschinenbetrieb. New theories, ad hoc rules, exceptions to the main theory, and then exceptions to the ad hoc rule that was invented to correct the main theory, and exceptions to exceptions. So yeah, that's what I wrote about, and with some success apparently. I stuck very much to what I think makes sense is well, the Zitterbeweging theory that was revived in the 90s, which is pretty much what mainstream physicist says cannot be done. Provide a sort of a local and very realist interpretation of quantum physics, of fields and charges and disequilibrium states. I will talk a bit about that more. I think for low energy physics, as I write here. I think the alternative theory is pretty much there. I mentioned I just bought this wonderful book. Let me see here. Unified Field Theory and Occam's Razor. It's written by a bunch of young and older authors. Some of them are a member of this Zitterbeweging Institute, of which I'm also a member. Well, it's not here. Here. It is kind of nice. It's a resource. It's I said it's non-mainstream and mainstream at the same time, in the sense that it does go back to before the Second World War, classical quantum mechanics, and it explains a lot of stuff in terms of what's written here, sort of simple solutions to deep questions, solutions about which you can argue, but they're explained in very simple terms, in terms of what happens inside the nucleus might be electromagnetic dipole fields. Dipole fields are asymmetric, but they're conservative, and the order of magnitude is what is what we would need to explain a nuclear force, what keeps protons and neutrons together, and that kind of stuff. And the anomaly in the magnetic moment, I said, the kind of thing that this guy is so enthusiastic about is, I don't know, this little figure, I guess, or not. Well, let me explain it here. Or not here. In any case, sort of, if the Zitterbewegung charge has a certain size, if we start modeling, particles in terms of having a definite size and a structure, then you arrive at nice things. I wanna show a few other things that sort of triggered my lecture. One of them is I get these NatureCom briefings, and this is from today. Smashing atomic and nuclear together reveals their shapes. You will say, well, that's sort of the standard stuff, but no, it's not. The way mainstream theorists have modeled high energy collisions is pretty much in terms of infinitesimally small particles, and infinitesimally small means zero size. How can something exist if it has no size whatsoever? And then particles, we know it's a misnomer. Since 100 years, you need to analyze things in the particle waves, or some kind of hybrid description, which goes back. If there's one paper you want to read, it's my most read paper, I think, here. High energy physics. I haven't pulled it up, but it's on the Breuil's matter wave, and that's very much in mathematical terms and charges and fields, and that's a very different description than. Let me go there than what I show here. Cars or particles crashing into each other, and then we see them disintegrate into many other parts, which in turn disintegrate until they come at rest somewhere, pieces of plastic and steel. Talking about that, because I do want to talk about the main topic of this lecture, and that's sort of this quark hypothesis. Do quarks exist? If there's one question, that I've always asked myself. It is this theory of quarks with partial charges and color charges and all kinds of other properties, new quantum numbers. That's the new theory that has been developed in the 70s, and we can see that in the last 5 or 10 years. That theory is under a lot of criticism. The whole standard model is under a lot of criticism. To show that I'm not the weirdest guy in the world. This is I found this. I visited a friend in hospital about a week ago, and there were a lot of magazines, and one of them is this Dutch, very fine magazine, EOS Wetenschap, EOS Science, and there was a number from 2019, special issue, Physics and Space, Fysica en de Ruimte, and it mentioned, I hadn't known him before, this Dutch physicist, Robert Dijkgraaf, who already 5 years ago in this article, which is a popular science magazine, says in 2019, the standard model is sort of unraveling, and it's no reason not to further invest in ever larger, higher energy particle accelerators. And it's very interesting. I didn't know that, but I looked him up, and he's actually the head of the Institute for Advanced Study at Princeton, where Albert Einstein and a lot of other Nobel Prize winners, more than 30 apparently, Oppenheimer, von Neumann, retired and could finally, publish or think about things without having the need to build up some academic reputation or move a team towards getting a Nobel Prize. And that's interesting. And in that sense, if there's one message that you should get from me is the contradiction between mainstream and non-mainstream theories. It is not what Sabine Hossenfelder or other people say it is. It is a crisis, yes, but within the mainstream academic community, there clearly is a lot of progress being made towards considering indeed simpler theories and questioning certain hypotheses. The problem is a little bit, another one I want to show is that I think the Nobel Prize committee in Sweden, unfortunately, has not always played a great role. A lot of Nobel Prizes are absolutely have been awarded for absolutely the right reasons, and I think it was in the spirit of Alfred Nobel himself said, reward experiments that come up with new measurements. Unfortunately, I think a lot of Nobel Prizes have been awarded for mere theories, and theories that later turned out to not be correct. But that's kind of difficult to admit that 10, 20 years ago, we rewarded CERN for discovering quarks, and then later you see like, well, maybe there's an issue there. The Nobel Prize committee is never going to award a physicist for falsifying a theory. It's going to reward a physicist or an academic for a new theory, and that's sort of a bit of a negative dynamic. I think what I pull up here, that an incredible 702 out of 736 Nobel Prize winners are really part of the same academic family. That suggests that there's a lack in diversity in these Nobel Prizes, and that they may not be the best guidance for an amateur physicist to say like, wow, this must be true because it's a Nobel Prize winner who said that. We all know that there was this Nobel Prize winner a few years ago who was a climate science denier. You see, these people are not always rational. They're beholden to certain dynamics, which are okay or not okay depending on your moral point of view. But it's not the best guide. Let me go back to my presentation. What I want to do really is is I covered a bit, low energy physics. I mentioned the books of Kovacs, Vassallo, Zitterbewegung Institute. I said these are simple solutions for complicated problems. I think the low energy physics, the nature of the electron, the proton as the two only, these are the two stable particles, matter particles that we know of. Their structure and their properties, magnetic moment, their size, the charge radius or their interaction radius has been explained. But it's really, what about the problem of the high energy physics, these disequilibrium states, as I call them. So I want to start a little bit or explain, the historical evolution of that idea and the explanations in that field. I'm going to talk about Feynman. He has only one lecture in his whole third volume, the lectures on quantum mechanics, that talks about that. That talks about these new quantum numbers that were invented to make sense of high energy particle collisions and decay reactions. So in 1963, and I'm going to talk about that, and I'm going to end with the last review of the particle data group from 2024. I'm going to pull it up, and I'm going to discuss, the logical, philosophical, I would say, or ontological inconsistencies. Feynman looked down on philosophers. I have a degree in philosophy. I have a few degrees, not in physics, but I think he was wrong to look down on philosophers. Your logical, epistemological basis has to be sound, and I'm afraid that the king of science in physics maybe doesn't have it right. Let me, before I go into my video, compare a little bit why we can't really think of particles disintegrating or decaying or colliding with other particles as a car crash. This image is spectacular. I love motorbikes and cars and engines. It's from the 2020 Daytona 500 race. Those cars are mainly Ford, Toyota, and Chevrolet cars. You can look up their make. They weigh about 1,500 kg. This was in the last lap when the accident happened, and you can see the car of Ryan Newman was touched from behind, and what happens is indeed the car spins totally out of control. You can see that all these cars weigh about 1,500 kg, have a lot of linear momentum, and suddenly you can see that linear momentum going in other directions. The car flies high up into the air. It spins around, it disintegrates. Some of the parts, stick together, the engine block and the cage of the car, because Ryan Newman miraculously survived this crash because he was in a cage. But you can see this is, high energies. The kinetic energies of these cars are calculated here. It's, the mass times the squared velocity divided by 2. It's classical. 4.8 million Joule. So that's a lot of electron volt. I noted here. You can calculate it. So what I want to say here is, these cars are very similar. At the same time, they're different, right? Probably looking from afar, it would be very difficult for you to tell the difference between a Toyota, a Chevrolet, and a Ford. Even these cars have they're not the same, and that's one of the things that I think when thinking about high energy particles, you need to take a lot of factors into account, and a small difference between two particles can make a big difference in terms of how they disintegrate. That's one lesson, I think. So when thinking about the different types of particles, I have a bit of a difficulty. Let me pull it up here. Yeah, here, this thing. This is the modern day classification where particles get lumped together. The old distinction between bosons and fermions has been broken up, I would say, or has faded away. We now talk about particles that consist of quarks, and I said I have a difficulty because quarks have never been observed directly. There's a lot of theoretical evidence for them, maybe, but they have never been observed directly. And still, we talk about mesons, counts, baryons, and then, on the other hand, photons, gluons, Higgs, they're all lumped together. I think there should be a lot more differentiation and senseful thinking about how we classify particles. On the other hand, we have these leptons. I'm rambling, so let me stop about that. But the thing is, like for an electron and a muon electron, an electron is stable, a muon electron is not stable. So in terms of what they actually are, for me, that would be a reason to carefully say, like, well, maybe an electron and a muon electron, they have charge in common, but there's a lot of stuff that they don't have in common. A muon electron is about 206 times the mass or equivalent energy of an electron. So why do we lump them together and call both of them leptons? And then we invent a lepton number or a lepton flavor number conservation law. I think that these are what some call phenomenological theories, where you wonder, like, okay, what do you mean by this lepton quality? Is it the commonality in what properties exactly? So the other thing you have to take into account, and I'm going to talk about that, is that obviously these cars here, they travel at, let's say, 150 to 180 miles per hour. What would happen if you multiply that velocity by a factor 1,000? The disintegration pattern would be very different. Probably these cars would sort of evaporate in many small pieces, much more rapidly, and in a very different way. And that's what basically we have when you think about the accelerators, like the Bevatron. I'm going to talk about that, which accelerated protons and let them collide with antiprotons or other protons at energy levels of, like, 6.2 mega electron volts. So that means they were accelerated up to an energy level that is 6.6 times the proton energy. We can you can't imagine that. You may try to imagine that, but these cars traveling at 200 miles per hour, their kinetic energy, I said, it's huge, 4.8 million euro, or but it's nothing as compared to their rest energy. In these accelerators, that's not the case. Most of the energy is kinetic, and so it is sort of a car crash, which is very hard to picture, to imagine. So I would say, if you're an amateur physicist, do try to think in terms of classical charges and classical electromagnetic fields, and that may help you to form a mental image of what might or might not be happening. And do realize that since 2008 or 2010, with CERN's Large Hadron Collider, we're now in a tera electron volt scale, so that's a factor 1,000. So that's like we accelerate protons and or other hadronic particles, let's say nuclear particles, to up to energy levels that are like 7,000 times instead of 6 or 7 times the mass of a proton, and that makes me think that a lot of theories are quite simple. Let me start with it. The strangeness number, I hope I don't have, but that's what Feynman and Gell-Mann and Pais were seeing in the early 1960s. A bubble chamber, and then particles coming out of high energy collisions from the Bevatron. And the first thing you note is that it's difficult to distinguish nuclear interactions from decay reactions here. You can distinguish them because, of course, after the fact, when you take all these pictures and compare, you can see, oh well, the charge conservation law has not been obeyed, so it must mean that there was probably here a nuclear interaction, and that this or that unstable particle took along a proton, which makes sure that the energy conservation law is being respected. So there's a lot of stuff I'm not going to talk about it. I had the intention to talk about that, but I'm already at 25 minutes, and I don't want to have a lecture of more than 2 hours. Probably going to be 2 hours. The thing that that Feynman talks about in his lecture is that is this thing here. I have the car crash again. Is that yeah, no. Here he said, we have reactions with these strange particles, as they are called. They used to be lumped together and called V particles. The V for this branching that you see in the bubble chambers. And then later we had this distinction between kaons and pions and a lot of other stuff. I'm going to talk about that. But the kaons are sort of, in many popular textbooks, these very elastic particles which can disintegrate into all kinds of things, including in short and long kaons, but what Feynman noted, I'm going to be short about it, he said, it's kind of remarkable that if you only apply the charge conservation law, you could theoretically write down a few reactions that could happen based on charge, energy conservation, linear momentum, angular momentum, your classical laws, but we don't see them happen. Like a positive kaon, which crashes into a proton, it could theoretically disintegrate into this. A negative kaon, a positive pion, and a neutral pion, which I think of as combining in some way positive and negative charge. That reaction as a whole respects the charge conservation law, but we don't see it happen. And there's other reactions here. He writes down a few. Now the thing is, and that's where I think his hypothesis doesn't make much sense, is that a number of these reactions have actually been observed to take place, and that's quite recent. I notice here there's a Na62. You can Google that. I will talk about the PG review. Yeah, we see very rare decay modes. We do see them happening. The branching ratio is of this order, an order of magnitude of 10 to the power minus 11. So they are very rare, but they do happen and they are real. This one as well, a long kaon, which Feynman didn't have a clue about, or at least he doesn't write about it. That was discovered later as part of this particle zoo. That's the other thing, this is supposed to simplify the particle zoo, but the particle zoo has only become more and more complicated. So to make a long story short, he sort of says like, okay, Gell-Mann and Abraham Pais, they supposed they associated the strangeness number to the antiparticle of a neutral kaon, a negative kaon, -1, and these we will give them a number +1, and then we have a proton and a neutron, but I'll show in the next table a lot of other baryons. I don't think this distinction between baryons and mesons is very useful. They both have they're the masses of the same order of magnitude, and so on and so on. But they get a number 0 together with all pions here, positive, neutral. These are particles with very different lifetimes, different masses. And for me, it's kind of strange, and it appears to be completely random, and I will argue it is, to say like, okay, well, to explain why this and this and this that does not happen, well, see it, the strangeness conservation law is not being observed. The strangeness conservation law is not being observed. You can immediately see this is a conservation law that is of a completely different I would say epistemological or ontological or philosophical nature than energy conservation or momentum conservation. But it explained the thing, and at the time, and it's why Feynman thinks this is a huge success. And then later, the strangeness law was not perceived to be sufficient to explain why this and that can happen in terms of decay or interaction, and this and that cannot happen. So then they invented beauty and bottomness. Beauty and bottomness are the same, or charm, all kinds of new quantum numbers. And The truth is, they haven't explained much. If you download the PDG 224 review, I don't know where I have it. Well, you can go to the PGG group and you can see the zoo, the particle zoo of unstable, the disequilibrium states. I will say a few things about what distinguishes a disequilibrium state from an equilibrium state, and why I think you shouldn't call disequilibrium state particles really. But I'll come there. It's the point is, these still confirm that most decays of or nuclear interactions, if you take out a whole, a positive or a negative kaon, will have a leptonic, as it's called, or semi-leptonic mode. Will disintegrate in a muon electron plus a neutrino, a neutral pion with an electron or a positron, or a neutral pion with a. That's 72% of the cases, and the other cases are here 28. It will disintegrate into another disequilibrium state, another unstable particle, and I said it's not fundamentally different. It looks the same, and then these pions, where we have here in 22%, it's going to be 2 pions. We have also 3 pion decay modes, slightly different, but that explains the other 28%. And then we have all these rare decay modes, which include the forbidden, which Feynman said this cannot happen, or golden modes it's called. We can now see they do happen, and that's where I think you should go back to the drawing table if you're an honest scientist or a community of scientists, and say like, okay, this strangeness conservation law doesn't work. We try to correct it with bottomness or beauty conservation and charm and a lot of other stuff, but it still doesn't work. And now we're inventing, it doesn't work because we have symmetry breaking. This new symmetries which are introduced by introducing strangeness and charm and other quantum numbers. It doesn't work, and so we invent another ad hoc rule saying like, okay, we have symmetry breaking, and in the symmetry breaking, we want to bring it all together again in sort of a supersymmetry theory or string theory. I think we should go back to the drawing board, and that's where I don't agree with someone like Sabine Hossenfelder, who says, yes, we need to reinvent theories, but the more recent theories have a lot of value. I'm not convinced. I think the theories of 100 years ago, before the strong force was invented, before people thought there was a thing like a weak interaction or a weak force. I mean, a force that explains disintegration. No, force acts on a charge, and so we have the electromagnetic force acting on electric charge, and there's no SI unit for a strong charge or a color charge or a nuclear charge. So perhaps there is no strong force or a nuclear force. That's what I argue for. Am I right? Am I wrong? I don't know. I know that these kind of answers make sense to me. They may not make sense to you. I'm not going to talk more about this. I have a paper because otherwise also I've been accused of using Feynman's lectures a little bit too liberally and not respecting copyright. It's an open source textbook, but then apparently it isn't because MIT has copyrights on it. Any case, it is in my paper, and I said this paper is the last one, high energy physics and disequilibrium states. Let me talk about that though. You can read why I think it doesn't make all that much sense. I promised to talk about equilibrium and this because that's probably the main thing or contribution I made in my crazy or not so crazy theories. The problem really is this, equilibrium states, low energy physics, as I write here. We can explain that by Maxwell's equations, the Planck-Einstein relation. There's all kinds of nice stuff here. We can explain stable matter and light particles, as I call them. We can explain photons, electrons and positrons, protons and antiprotons, and we've come quite far with the theory of the neutron and anti-neutron, some kind of combination of positive and negative charge, a proton positive proton with some kind of neutronic negative charge, and then the other thing, an antiproton with some kind of neutronic positive charge. So that's why a neutron and an antineutron, they're not the same particle, even if they're both neutral. So we've come quite far with that. The thing is with high energy physics, and that's the problem, is in classical theory, we've learned to model disequilibrium states in various ways. But in a way, this is the metaphor. We will think of it as being a regular cyclical oscillation, and we will say there's some kind of damping or friction, and so this situation is not stable. There is some damping going on, and then we have this thing peters out, so to say, and that's not working. That works probably, or might work, I haven't examined that, to explain like a mean lifetime. Or an average, and we have very finely measured data, the core data values for averages, for mean lifetimes, which are very short. But it doesn't explain that sort of also where you say, oh, you don't like Feynman diagrams. I do actually, because this would be my most simple Feynman diagram, where we say, okay, we have here a short neutral kaon, right? And we know that in 99%, or in a lot of cases here, yeah, here I have it, in a 70% of the decay reactions are two pions, a neutral one and a positive one, and the other ones are, it decays into two neutral pions in about 30% of the cases. So yeah, that's a Feynman diagram. I put this one here, and it explains that what happens here in almost 70% of the cases. We have this kaon, it disintegrates in two parts, and what explains the exact lifetime of this reaction? I'm not talking about a mean lifetime, but its exact lifetime. And for that, we don't have a model, honestly, in mathematics. That's exactly the difference between a disequilibrium state in classical physics, I would say, and in quantum physics. At some point in time, there's some kind of I wouldn't call it a hidden variable, but well, let me talk about that. Why wouldn't I call it a hidden variable? Because I think it's about this car crash. We know the laws of mechanics. Here, this car crash, right? But we can sort of, even in our world, this little hit it took from a car that came from behind. That's a very tiny energy transfer, I would say, or disturbance of the system. And you would say, yeah, of course, it's totally unpredictable if that car is going to go left, high, or right, if it goes 20 meters up in the air or only 5, and in how many parts it disintegrates. That's actually the true nature of quantum physics. This is the metaphor, I would say, is it's statistical determinism. We do not know. I don't believe, like Sabine Hosfire, that you have an infinite chain of causal, an infinite causal structure here. No, it got hit. It was a tiny disturbance of the system, and the reaction is totally unpredictable in the sense that it's not statistically unpredictable. It's unpredictable in the specific case of this 2020 Daytona 500 crash. We just don't have all the relevant information. And that's why we cannot exactly predict how this car is going to disintegrate. And so that's the thing that you have in a Feynman diagram, I think, is it is the same. And I'm not so worried about it. I don't think we can go beyond. I think that's the revolution of quantum physics. And the whole thing about the Heisenberg-Bohr interpretation of quantum physics is that they say we have to be content with statistically deterministic models. And for me, that's okay. If you interpret Heisenberg-Bohr, die ist ein unendlicher Quantenphysikbetrieb, Wurstmaschinenbetrieb like that, then I'm fine with that, because that's correct. And Ehrenfest should not have made a fuss or committed suicide on this thing, because it is what it is. But so mainstream physicists, they're academics, they have to publish, and so they do try to come up with something that would precisely explain what happens in which situation, and that's where they come up with these quantum numbers, new quantum numbers, strangeness and stuff and whatever. I don't think it makes sense. So I've been rambling. I would say go to my paper, read it if you're interested in that kind of stuff. But the message is that unlike what Sabine Hossenfelder says, is that a lot of theories that have been invented in the last 40, 50 years make sense, and it's just a matter of picking out the right one. I don't think that's ever going to happen. We need to go really back to the drawing board, and yeah, I'm done here. Really go back to the drawing board, and that's what's being done, for instance, in this book here, Unified Field Theory and Occam's Razor. I bought the book because I'm ambiguous about the book and not mainly not. This is really talks about Maxwell's equations, a lot of stuff that where you can combine classical electromagnetic theory, bringing in the Planck-Einstein relationship and come to a set of equations that does not invoke strong force, nuclear stuff and whatever. It explains a lot. I do not agree with everything I said. The electron model here or the proton model here or the explanation of the anomaly. What it shows is that there are no hidden variables indeed, and that rational, local, and realist explanations for everything that has been measured in or has not been measured, that's equally important, over the last 20 years is can be explained in a rational way. But yeah, using a statistically deterministic model rather than there's a logical inconsistency in the I would say what goes as the mainstream interpretation, because I'm not even sure about the mainstream interpretation of Heisenberg Bohr principle. It's if you go on Wikipedia, it's kind of fluffy. If there's regularity, if we say that wave functions, probability amplitudes, and probability functions, if we take the absolute square of them, if we get clear and unambiguous mathematical functions out of them, then it's nonsense to say that, oh well, we get these probability functions, but there's nothing that explains these probabilities. I mean, tell me, how can you get a regular mathematical function for a probability function if there's no underlying physical phenomenon that explains the probabilities? For me, that's the biggest and the single most important mistake, or it's what the gurus, and gurus are both amateur physicists, but a lot of academics as well, who sort of continue the myth to say like, oh well, there's something God-given there that we don't understand. There's nothing God-given. Religion is religion and physics is physics. If you get regular functions, I'm going to say it again, for probability amplitudes and therefore for probabilities, then there must be a physical explanation for it. And that physical explanation is probably, and for me surely one, it's statistically deterministic. We don't know the initial conditions of the system. We have a regular oscillation, but the oscillation, the frequency is so high that we don't know, its cycle time, but we don't know what the argument of this wave function is at this very moment. We can say it is going to be between this and that, and it has a cycle time, and that's it. And I don't think that is very mysterious. Let me go to a few other things. Let me wrap up my lecture. I said this one is interesting. I'm really happy because for many years I follow like nature and what comes out of all these experiments, and I see it's becoming a lot more sensical. There's also a lot more self-doubt, I would say. It was very heartening last year to see that even my view is quite dualistic. I believe in charges and fields, and so then people tell me like, yeah, but an electron and a positron, it produces two photons. So where does the charge go? I have no answer to that, and I know I'm in a minority to sort of say like, well, maybe the two photons that come out of that reaction, lepton colliders, electron and positron colliders, they operated for a very short period of time, and then they were replaced by hadron colliders. Maybe, yeah, I can show that the list of hadron colliders. That's interesting to see. They moved to. But if you look at the experiments of early electron, the Chinese are going to rebuild a lot of these things in a much larger scale. I hope that one day, that's my hypothesis, these photons aren't real photons. Maybe they are the W plus minus bosons and the neutral Z bosons that have been discovered. Because I believe bosons are real. I don't believe quarks are real, but these bosons, there was something there. It was measured, and that's kind of unambiguous. It's just like these bosons weren't probably bosons. They were fermions, they were matter particles, unstable matter particles, and they behave like photons in the sense that they have no charge, but they don't behave like photons in the sense that they have a theoretical rest mass. They're massive, and so that makes me think that maybe they carry two charges, which positive and a negative one, or a positive one in case of a W plus boson, and that sort of stuff that you see happening now, where physicists doubt the conclusions that their predecessors, even if they're Nobel prize winners, were, say, well, your photon there, was it a real photon? And these are the right questions to ask, and I'm happy about this. And this is also where I would say stay tuned. And nature.com subscription doesn't cost a lot, and you will see a lot of hidden figures. Yeah. These things do say like, okay, we can see a lot more now than we could see 10 or 15 years ago, and that's nice, and that's where I'm with this Robert Dijkgraaf, to say that we should keep investing in sort of these large experiments to find out more. Discovery is probably the most unique thing about the adventure of the human mind. There's another one here. I talked about that. I talked about the Sitter Institute. Yeah, just to say like, okay, I'm a member of this thing. Also here you should read it with a grain of salt. Like, I mean, this is a guy I admire enormously. He's much more famous than I am on electron models. We still aren't finished with them. They're different ones. The way he explains these 3D trajectories of charge, while he talks about energy, is also like, I'm saying like, okay, what's energy for you? At least make the distinction between the kinetic energy of a charge and the potential energy or field energy that acts on the charge. And so it's not that I uncritically subscribe to what all that is being presented here. I'm just saying like, this is interesting. This is an alternative, and it is what these people say that they are trying to do. They try to come up with simple or simpler solutions in the sense of providing, realistic models, models that allow you to imagine what might be happening. So yeah, I'm not going to talk about that. That's an old book, Lederman. The Tools of Discovery. I would recommend it also. As an amateur physicist, I think I got lost, and I probably lost like 5 years of that, by not investigating, the tools of discovery. What can you see in these accelerators, and why would we need higher energy ones? The things I said, that the energy difference between the Large Hadron Collider in CERN and the first Bevatron, that's a factor 1,000, and think about that and try to imagine what it might imply in terms of new discoveries, rather than immediately trying to find a theoretical model that explains it. I think there's been not enough investment in experimental physics and too much writing. I mean, the number of journals in physics, and it's just, you can't keep track of everything that's being written. So I also stopped writing because I realized I talk too much and don't read enough. We talked about this book as a good example. I just want to say one more thing about unified field theory. So the book proclaims to, and they do talk about that, unified general relativity theory, the theory of gravity with electromagnetism. I don't know if that's a useful attempt, but if you're into that, I'm not into quantum gravity. I think the energy levels are enormous when you go to smaller scales, but I don't think. We're not modeling black holes, but the math is interesting. Yeah, I really warmly recommend that book. And the math, Clifford algebras. And if you want to learn new math, this is the book to go. Wikipedia, I say Wikipedia is quite good on facts. It's not good on mainstream, on the standard model. And it admits in a way that I try to contribute to Wikipedia articles, trying to promote a little bit this Titelbeweging theory or my local and realist. You just don't get through. What you find on Wikipedia is the standard model, nothing more, nothing less. And if you think the standard model doesn't make sense, like I do, then Wikipedia doesn't make much sense. But I regularly consult it, and I can recommend you to do that also, to find a reference to the things that have been measured. The hadron and classification mess, I talked about that. Yeah, unfortunately, the Nobel Prize. I'm going to refer to my blog a little bit here, where I think I'm, at the same time, I'm more, I mentioned Sabine Hossenpfeiler. I'm at the same time more radical than her, but also more moderate. I don't think it's very useful to sort of portray current debates in terms of, oh, well, this is the big discussion between mainstream and non-mainstream. And then like Sabine, when you say mainstream theories don't make sense, but I do believe in infinite causal structures. I do believe in quantum gravity. I think string theory makes more sense than supersymmetry theories. I mean, I'm just quoting a few things of recent videos of her. Then I go like, well, you actually do leave your viewer, and she has millions of them, I only have a few hundred, with many more questions than answers. And I don't think that's good for anyone. I don't think that's good for the credibility of academics, of the science establishment, but it's also not good for the credibility of Sabine or me in a very minority, trying to say like, hey, the math is interesting, and I think we can bridge some of the theories by focusing on this question. This is a mathematical model that corresponds to what we measure. How should we interpret the mathematical model? What concepts are behind? And I said, unfortunately, concepts like these new quantum numbers, quark numbers, they are very difficult to fit to what's being measured, to what you see. So this is my rant. I said I do recommend. I said I was happy with the 50,000. There's a lot of stuff on Vixra still. I switched. I also have a few 10,000 reads, but The Emperor Has No Clothes, maybe. That's a manuscript that I don't have on. You can see I put a lot of work on it, many different versions, because I did have a publishing contract with WSP and Morgan Claypool. Unfortunately, it didn't survive the review. But this is sort of an easy introduction. Okay, it's too verbose, the beginning, on the fine structure constant. How could we interpret it? This Titelbeweging particle, my rant that all these modeling of spin zero particles, well, spin zero particles do not exist. The very nature of light and matter is spin, and the spin is real. It's a curl of a field, and it's the angular momentum of charge and photon experiments. So that's one I would recommend while I'm saying indeed goodbye to my hobby. What else is there? Showed that. Thanks. I don't know who you are, but thanks for introducing me into the Anagalactic Hall of Fame. And keep reading and keep thinking for yourself, I would say. I said this guy is very promising, Robert Dijkgraaf, and I'm really sorry I sort of missed what he wrote and said. Apparently, he comes regularly to Belgium, also to the KU Leuven. where my kids studied. And I honestly, when I saw what he wrote in 2019, where he plainly said the standard model is unraveling, we just don't have a theory that's sort of ready to replace it. Congratulations, that's nice, that's honest. My thing is, let's go back to where things went wrong. Yeah, academia, I have some reads there also, but I really moved. I think, I mean, talking about these fora, Vixra and academia.edu and ResearchGate is nice. You are with 25 million other researchers there. The way they organize debates, questions, join in them. Just sometimes, like I do, disengage when you feel that people take their own views too personally. I want to finish perhaps with this thing. You will say like Hegel. What is this here? All cats are gray. What I found, and now I'm really talking as a philosopher, I think our current thinking and the crisis of science is a bit like I said. I'm the first one to say like try to explain things in a way that everybody understands by invoking 3D space and unidirectional time. Call things for what they are. But at the same time, calling we suffer from what Hegel in 1807 to the phenomenology of spirit. Sorry, I'm a Dutch speaker. I think we do suffer from sort of an attitude where we're looking at things and we call it we homogenize our concept, and then you end up with sort of what Hegel said. You end up with walking through the night in which all cows are equally black. Apparently, that comes from a popular proverb which says the dark, all cats are gray. So then you think about Schrödinger's cat. We should, where he said it describes a condition in which all particulars are indistinguishable, and Hegel thought that was very inadequate in Schelling's theory about the absolute. I agree with that. Don't be too fond of your own theories. I said it's one of the reasons why I'm holding off, and I'm in a minority within a minority in this Twitter Institute where we say like all is energy, or all our fields, some kind of unified fields. No, there's electric charge and electromagnetic fields, and there's gravity, and it's not because we have quantum physics in quantum physics that gravity would not be what Einstein said it would be a fetcher of the universe, a geometrical fetcher of the universe. For me, that's okay. Make those distinctions, and it's going to make you a very happy person, because that's what I want to conclude with. I've been very happy exploring all that stuff. I would recommend to people like me who start in this journey that I started like 15 years ago, trying to understand. Like, keep it fun, and again, don't think the truth is somewhere out there, and that you're the only one who happens to stumble upon it. That's gonna make you very unhappy and isolated. And I think one of the good things is that I was read, I engaged with a lot of people. With most people, there is a disagreement on, or it ends sort of in a fuzzy debate where in the end you say, I believe this and you believe that, and that's fine. And these beliefs are ultimately what Hegel talks about. These are mental concepts and things that you are comfortable with, while other people are comfortable with very other philosophical outlooks and concepts. And there you have to give up and say like, the truth is probably somewhere in the middle. And I'm gonna upload this, and that's gonna be it. I thank you guys very much. I said this was fun. Thanks for reading me. Thanks for watching me, although you'll never get to the end of this video, I'm sure. But that's what I try to do is pave the way a little bit and try to do a lessons learned on things to do and things absolutely not to do when you try to do what I try to do, and it is to see what makes sense and what doesn't. And the only way you can do that is try to make these models your own, not in a sense that you absolutely want to understand them, but you understand them in a way that you think like, okay, I see where this comes from, and I don't agree with it because, like in this case, this strangeness number appears to be a very ad hoc hypothesis, and later experiments proved that the experimental facts between brackets on which Feynman and Gell-Mann and Pais based themselves to come up with this ad hoc hypothesis were turned out to be not correct. And then you see a series of academic scientists, because they are academics, and I said there is a bit of there clearly is a mainstream view, the standard model, and they follow the herd. And so don't follow the herd. At the same time, make sure that you don't get isolated from the herd. So the difference between, my brother told me that once, is the difference between a crackpot theorist or a crazy guy and someone who's non-mainstream is probably a real crackpot theorist or a real a crazy guy. He finds himself sitting in a corner and everybody around him says, well, this guy is not making sense. I think a non-mainstream theorist is someone who about whom a lot of people say, like, we don't understand what he's talking about and it doesn't make much sense to us, but it's kind of interesting and he's engaging, and we do look at him as perhaps bringing some kind of new point of view. And on that point of view, maybe not on the detail of his theory, but on that point of view, we can have a sensible discussion of what makes sense in terms of concepts and what not. And that will be it. I am indeed at exactly 1 hour, which is great because I thought I would be talking for 2 hours, and I did not. So that's an achievement. I wish you a very nice day and a wonderful weekend.